Welcome, friends. We are discussing network theory. Uh, Today, from this session, we will start a new topic, which is the seventh module of this course, which is transient response of electrical network. Now, module 7, 8, 9, it's all about the transient response of the electrical network. Now, any network which undergoes some transient state, that problem, or you can say the current flowing through or voltage across any element under transient state, can be solved by using two methods. Either we can approach time domain approach, or we can solve that problem using frequency domain approach. So 7, 8 module, 7, 8, 9, these three modules from now, we shall mainly discuss the transient behavior of the electrical network, and we shall discuss mainly two methods by which we can solve this type of problem. So let us first try to understand what is meant by transient. What is meant by transient? Okay. First, let us say we have a network. Let us say we have a network. Any network, any electrical network. And now that network should have some voltage source. Okay, should have some voltage source at the input terminal. Should have some voltage source. Now this voltage source, let us say this is V in. This voltage source, let us say it is kept open circuited. That means it is not energized. The network is not energized. Now to obtain a current or to have the voltage across any element, you need an energy source to feed energy into the network. So we assume V in, that is the voltage source that feeds the energy. Now the moment, this is a switch, right? This is a switch. Now the moment I make it closed, that means the switch, it is closed. You see the current starts to flow. Current starts to flow. Some current will start to flow. So what is happening actually, the network is suddenly, it was initially is at off state, it was initially at off state. Now due to the pressing of that switch from off position to on position, it is now in on state. So this is turned from off state to on state by just pressing a switch. So the network is undergoing certain change, a fast occurring change it is undergoing. So that fast occurring change, if it is stay within that network, or it experience that network experiences that change, certain change, as a result the network feels some discomfort. So in the language of electrical engineering, we say that discomfort is actually called transient state. It's actually called transient state. Meaning, suppose for any human being, if we stay for a long time in a dark room, and if we suddenly come across the sunlight, then our eye does not accept sun immediately due to our human nature. So that I is suddenly undergoing from dark state to bright state. So that is why that we suddenly momentarily a disturbance disturbance is created within the eye. So we say that it is true for anything, it is true for any object. Okay, if any object experiences certain change, quick change over a time or for a very brief time, so that object experiences some disturbances, or rather in layman's language we can say that object is experiencing some discomfort. So in electrical engineering we say that discomfort is called transient state. So whenever we press a switch from off state to on state, the network is undergoing a transient state, right? So this is transient, means you can say it is a disturbance, right? Transient meaning, so transient behavior, that is transient response, the name of the chapter, it refers, that is the, it is disturbance caused by the pressing of switch from on off state to on state and vice versa. It can also happen from on state to off state, right? So if we switch off any network from on state to off state, the same thing, the network will undergo some sudden change from on state to off state. So it can happen in both the ways, from off state to on state and from on state to off state. In both the ways it can work. So now we will discuss that if a electrical network have some that switching phenomena, if that electrical network having that switching phenomena, how that electrical network will behave. Okay, so that electrical network, as of now, inductance and capacitance are very important parameter, two elements of an electrical network. So we first, let us try to understand what is the behavior of an inductance during transiency, and thereon we will study the behavior of a capacitance during transiency, or instantaneous behavior we shall study. Okay, now as you can you all know that voltage is according to the Faraday's law of electromagnetic induction, V is equal to rate of change of flux linkage. Okay, rate of change of flux linkage. So from there we are discussing the inductance, behavior of an inductance, right? So you know that so from this equation, V is equal to d psi dt. So what can be written? Psi is equal to integration V into dt. Okay, V into dt. Now I must put my limit from minus infinity to t. Minus infinity to t, right? Now I am breaking this integration into two parts. One is minus infinity to 0, V into dt, plus next integration 0 to t into V dt, right? So this actually, now if we assume, or if we consider the switch is changing its position from off state to on state, now we refer that timing instant of that switching is t equal to 0. That means we need to consider, or we need to calculate or analyze the behavior of the network from the instant of switching, and then we refer that time is equal to t equal to 0. Okay, now anything integration V dt from minus infinity to 0, it refers as a negative time. It refers as a negative time. Okay, it refers it to be a negative time. That is integration t minus infinity to 0, that means it's the negative time. Now, what is negative time? Negative time means it is before switching. It is before switching, right? And after switching, this is the expression 0 to t v dt. So, if we write this expression, that phi, that is flux linkage, that will be equal to psi 0 plus integration 0 to t v into dt. That is a very important equation. Psi 0 is this, actually psi 0 is this, minus infinity to the 0. So phi 0 is nothing but it is the initial flux linkage in that inductor. Okay, phi 0 is the initial flux linkage in that inductor. So when an inductor is in operation in a network, whether we have a flux linkage in that inductor initially or before the switching has been done, to understand that fact we will assume this term psi 0. Okay, so if there is no flux linkage prior to the switching, then psi 0 is 0. If there is some flux linkage prior to the switching, to account that term we are considering psi 0. Okay, so from this equation actually we can understand or we can analyze the behavior of the flux change by this graph, figure 1a. So what is that equation? Psi is equal to psi 0 plus integration 0 to t v into dt. That means this equation actually tells that, or actually signifies that over some time flux linkage building from initial value psi 0 to the final value psi. So we have initial flux linkage psi 0 at t is equal to 0. This is t is equal to 0, and we have final flux linkage of psi after some point of time. Okay, so from 0 to t second we have flux linkage from psi 0 to psi, and from this equation we can understand that it will follow a linear curve. It will follow a linear curve like this. Okay, it's very simple. And now if we consider these 2 points, actually point number 1 and point number 2, they are very close to each other. There, point number 1, let us say point number 1 has a flux linkage of psi 1 and point number 2 has a flux linkage of psi 2, right? So we are assuming point 1 and point 2 are very close to each other, so their time difference is almost 0. So this delta t is almost 0. It is 10 to 0. Okay, so we can say quite logically, rationally we can say that this psi 1 and psi 2 are almost equal. Psi 1 and psi 2 are almost equal as delta t tends to 0. This we can say from this diagram, because as these 2 points are almost closer to each other, almost they are very nearer to each other, as this delta t tends to 0, then we can say that they are almost same point. So in that respect we can say psi 1 and psi 2 are almost same, not exactly same. Technically it is not possible, but they are almost same. So if we can say that what is psi 1? Psi 1 is equal to L1 I1, psi 1 is equal to L1 I1, and psi 2 is equal to L2 I2. But we are considering only one inductor, so we can write this psi 1 is equal to Li1 and psi 2 is equal to Li2. So from there LL cancels out, so we get a very important result that I1 is equal to I2. So what does this signifies? That hence it can be concluded from the current, it is concluded that current flowing through an inductor does not change instantaneously. I repeat, current flowing through the inductor does not change instantaneously. That means if there is a conductor, there is an inductor, we are having a switch. So if there is some current is flowing, I1, okay, or rather say I1, and if we say if that current is flowing after the switching, just after the switching, I2, it is there same. Okay, switching has been done is equal to T is equal to 0. So this term is very important, instantaneously, right? It is a momentary, it is true for instantaneously. If you take from this diagram, you can understand one thing, that if this delta T is large, then psi 1 not equal to psi 2. So this psi 1 and psi 2 only be equal or almost equal rather for delta T tends to 0. So delta T tends to 0 means it is an instantaneous behavior. It is instantaneous behavior. Okay, so it is true for instantaneous event. So if a inductor is there and current flowing through them, it does not change instantaneously, right? So that is the statement. Now let us try to understand more technically, that suppose we have this is a switch, right? We are making it close from we are making it close at T is equal to 0, right? So switching instant, we refer switching instant, we refer to be T is equal to 0. Okay. So now this T is equal to 0 can be thought in two more different ways. That means switching instant T, that is equal to 0 minus, and that will be equal to 0 plus. What does it 0 minus stands? 0 minus stands just before the switching. Let me make some more space. Switching instant T, first of all, it can be is equal to 0. What is 0? T is equal to 0 means at the instant of switching. At the instant of switching, right? That is the meaning of T is equal to 0. At that moment, okay. Now again, T is equal to 0 can be again split into that, it is 0 minus, okay. So T is equal to 0 means just before the switching, just before the switching. Lastly, we can say T is equal to 0 plus, it is just after the switching. So that switching instant is split into three parts. Technically, mathematically, they are same. Mathematically, they are same. That is, quantitatively they are same, but qualitatively they are totally different. We say, when we say that momentarily or instantaneously current flowing through the inductor does not change, that means we mean that just current flowing through the inductor just before the switching and current flowing through the inductor just after the switching is same. So we write in this fashion, I at t is equal to 0 minus, that is equal to I t is equal to 0 plus. That means current flowing through the inductor just before the switching and current flowing through the inductor just after the switching are same. So this term is very important, just. Although they are all pointing the switching instant, but purposefully we have split that switching instant into three parts. At the instant of switching, just before the switching, just after the switching. Quantitatively they are all same, there is no difference. However, qualitatively 0 minus means just before the switching and 0 plus means just after the switching. So we can understand from this figure 1a that instantaneously flux linkages are almost same. So from there, psi 1, psi 2, we can understand that current flowing through the inductor does not change instantaneously. So if we take instantaneous time duration, so whatever be the current, it remains same. However, if you don't take or if you don't consider the time to be instantaneous, then of course current will change. So this is a very important parameter or the important property of the inductor. So that is very important. Okay. So it is the current flowing through the inductor does not change instantaneously. Okay. Now let us proceed this discussion. What happens to the capacitor? Now in case of a capacitor, we can write the equation as I current is equal to dq by dt. I is equal to dq by dt. So from there we can extend this analysis just like previous way. Q is equal to integration I into dt. So integration should be, normally we refer it from 0 to t, but in this case also we will assume minus infinity to t. And from there we will break this integration into two parts, minus infinity to 0 I into dt plus 0 to t I dt. So this refers to be the charge at some negative time. That means it is referred to the before switching phenomena. And this will be the after switching phenomena, right? After switching phenomena. So as a result, we can write the similar sort of equation is equal to Q is equal to Q naught plus integration 0 to t I into dt. What is Q0? Q0, as you know, Q, that means we are discussing capacitance. Capacitance is a charge storing device. So Q0 refers to initial charge stored by the capacitor. Initial charge stored by the capacitor. So when a capacitor is in operation in an electrical network, we don't know actually whether it contains some initial charge or not. So if it does not contain an initial charge, then Q0 becomes 0. However, if it really contains some amount of charge, to understand this fact, we consider this additional term Q0. So again, if you consider figure 1b, so we can present the similar, or we can represent the similar sort of analysis. So we have started with some initial charge, and over some time t, final charge build up till q, where initial charge was q0 at t is equal to 0. So again, if we consider 2 points, point number 1 carries at point 1 it is charge q1, and for point number 2 it carries a charge of q2. So the same result, it is a very close to each other, these 2 points. So as delta t tends to 0, So we can say that Q1 is equal to Q2 or almost Q2. So as you can know, Q is equal to CV. From there we can write CV1 is equal to CV2. So from there V1 is equal to V2. So what we can understand from the capacitance behavior is that voltage across the capacitor does not change instantaneously. Voltage across the capacitor does not change instantaneously, right? So we write in this fashion Vc T is equal to 0 minus, it should be is equal to Vc T is equal to 0 plus. So instantaneously voltage does not change. So we have understood two fundamental properties of inductor and capacitance. What we can observe from the inductor, current flowing through the inductor does not change instantaneously, number one, and from the capacitor we have understood that voltage across the capacitance does not change instantaneously. Okay, now by using this fact or using these two very important and fundamental properties of inductor and capacitance, now we try to understand what will happen under transient state. Okay, now there could be two types of states, right? So, suppose one network is there, it is connected to a supply, it is connected to an energy source, at some time t is equal to 0, which is called switching instant, right? So at t is equal to 0, we refer t is equal to 0 as transient state, quite obviously, because it will undergo some disturbance. Okay, now after having done the switching, if the network is connected to that voltage source for a longer duration of time, then we can say that when t is equal to infinity, okay, when t becomes infinity here does not necessarily mean that it is in a true sense it is infinity. T here stands infinity means it's a large time, maybe 5 second, 10 second time, it's a large time, right? So if a network is getting some energy from an energy source for a longer duration of time, then we can say that t is equal to infinity. That means that we say that network reaches to steady state. Network reaches at steady state. So that means it is working quite stably. No disturbance is there to perturb the performance of the network, right? So we fundamentally understood at t is equal to 0, we have a disturbance to cause. That phase is called transient phase. Okay, and when that network is getting energy supply from a source for a long duration time, that means time has elapsed, a considerable amount of time has elapsed from the instant of switching, we say that the network is reached at steady state. That means network is operating stably. Okay, no disturbance is there. So if it is okay to you, then we can say that let us consider this network, figure 2a. We have an inductor L. If we have an inductor L, now please try to understand that. You see, this is actually switch, this S. Okay, this symbol refers to switch, this arrow, straight arrow. However, this curved line represents the direction through which switch is operated. So this direction means switch is operated from off position to on position. So it means switch is from off, it is now make at on. So switch is closed at t is equal to 0. Now before switching, the switch is at this position, right? That means switch is at this position, that means inductor has no current in it, right? Inductor has no current because this is open circuited, so current flowing through the inductor is 0. Now the moment it is switched on at t is equal to 0, what will be the current flowing? So due to this fact, current flowing through the inductor does not change instantaneously. We say that current flowing through the inductor I0 minus is equal to current flowing through the inductor just after switching will be 0. So this is the thing we can write from the fundamental property of the inductor. What is that property? The current does not change, current flowing through the inductor does not change instantaneously. I0 minus is 0. Why? Because prior to the switching, circuit is or inductor is isolated from the energy source, so current flowing through the inductor should be 0 because it is open circuited, switch is open. So if a switch is open, no current can flow. So now as you just close the switch, so if you consider that time only, so it is I0 plus, so just before the switching, just after the switching, so that should be is equal to 0. So now 0 current, no current is means it is a open circuit. It is a open circuit, right? So we can say that in the transient state, when a network undergoing to transient state, so an inductor, it should behave like a open circuit. It should behave like a open circuit, right? Transient state. That is the proof because no current is flowing through it. Okay. Now just consider the reverse phenomena. The switch is closed for a long time. And now due to the switch is closed, some current is flowing I through the inductor. Okay. So now at some different time, we are making another switching operation. Now we are making the switch from on position to off position, which was initially at on position. Now we are making it off. Okay, just as if fan is moving, we are shutting it down. Okay, or light is glowing, we are making it off. Just like that, from on state to off state, we are converting. So just before the switching, what is the current flowing through the inductor? I0 minus, it should be capital I, that is the full current is flowing or huge current is flowing. So as per the property, current flowing through the inductor does not change instantaneously. I0 plus will also be equal to 0. Although it is open circuit, just after the switching, some current will flow through the inductor because of this fundamental property of the inductor. So you can see current flowing through the inductor is a high value. So that means you can say that under steady state condition, inductor behaves like a short circuit. Because it carries huge current. So we can understand that at transient state, an inductor behaves like an open circuit, and in steady state it behaves like a short circuit. That is the explanation, logical explanation. Now let us discuss the capacitance behavior. We consider the same figure 2C. Initially the capacitor was open. Okay. Now since the capacitor was open, so no current is flowing, so I0 will be 0. Okay. So no current would be flowing. So if there is no current is flowing, capacitor cannot develop voltage across its plates, right? If current is zero, then capacitor cannot develop voltage across its plate. So due to that fact, we can write Vc 0 minus. That means just before the switching will be 0. Now if we making the switch closed at t is equal to 0, so from the same logic we can write Vc 0 plus is also equal to 0, because voltage across the capacitor does not change instantaneously. So what does it mean? Zero voltage can only occur in case of a short circuit. In case of a short circuit. So if you consider a capacitance, so if a network undergoes a transient state, then that capacitor would behave like a short circuit. Okay, just you can replace that capacitance by a short circuit. Okay, that is the explanation, because zero voltage means short circuit. Now again, if we consider the steady state, suppose now switch is closed, so the current is flowing, so voltage is built up across the plates of the capacitor. So that voltage is, let us say, V, because the supply voltage is flowing or falling on that capacitor plate. So we can write Vc 0 minus, that is equal to V. Now the moment you open the circuit or open the switch S at t is equal to 0, just after the switching it remains at V. Just after the switching it remains at V, because voltage across the capacitor does not change instantaneously. So although it is open circuited, the full voltage is appearing across the capacitance. So when across an element full voltage comes, it is when that is behaving like an open circuit. So if you consider the steady state, it behaves like an open circuit. So for a capacitor, we can understand that under transient state, it behaves like a short circuit, and in steady state it behaves like an open circuit. So we have understood, we have discussed the few fundamental properties of inductor and capacitance under transient condition. We have found that fundamentally, if you consider the transient behavior of the inductor and capacitance, current flowing through the inductor does not change instantaneously. Here instantaneously is the key, and voltage across the capacitor does not change instantaneously. So by using this fundamental property, we have analyzed our network, and we have found when a network undergoes a transient state, that means when an inductor comes and fills that transient state, that immediately that inductor will behave like an open circuit. And if that same inductor is experiencing steady state, that means a network is operating for a long time, that means that network has been reached a steady state, then immediately inductor will operate like a short circuit. That means inductor will offer zero resistance or zero impedance rather. So under transient state, inductor behaves like open circuit, and under steady state condition, inductor will behave like a short circuit condition. On the other hand, if you consider a capacitor, and if it undergoes some transient state, it is behaving like a short circuit, that means it will offer zero reactance to the network, and under steady state condition it will operate, or it will act like a open circuit. So these are the fundamental properties of the network elements, inductor and capacitors, under transient state and steady states. So I am ending this part here. From the next session we continue this discussion. Thank you.